Okay, this is what we stopped last time, and we want to prove this claim. The claim is a subtree rooted at the node x contains at least two powers the black height of the x minus one internal nodes, and we are going to do a induction. And the base case will be, well, if x itself has the height of 0. So if a node has a height of 0, and we are talking about the Reb-Black tree, and that is a fake leaf, or, well, we can say it is a null leaf node, because that is not usually the leaf we are talking about. That is the additional level of the leaf we added in the Reb-Black tree. So what is the black height of a fake leaf, or a leaf which represents a null pointer? Well, if we don't want to consider the current black node we are visiting, and that is a 0. So this subtree contains 2 of the black height x minus 1. So let me bring up the laser pointer. So 2 to the black height of the x minus 1, and that is 2 to the 0 minus 1, and that is 0. So the claim holds in the base case. So that is the height of the x is a 0. So if you want to move on, and we want to, inductive step will be, how about x has a positive height and 2 children? And then, well, for each of the children, well, it has the black height to be either the same to the black height of the parent, or the black height of the parent minus 1. So why those two cases can happen? So let me go back to this example. So for example, if we are using 14 here, so the black height of the 14 will be 1, 2, right? So if we exclude the 14, and then the black height of 14 will be 2, guaranteed, no matter which path you want to go down. And then how about the height of the 2 children? So the black height of the left child will be 7, and now. So the black height of the 10 is 2. However, if we see the 16, and then the black height of the 16 is a 1. So let's come back to this argument. So each child has a black height to be black height of the parent, or the black height of the parent minus 1. So why it's like this? Well, the reason is we are painting the colors differently. So depending on the color of the children, well, if it is a red child, and then it will have the same black height as the parent, or if it is a black child, and then the black height will be the black height of the parent minus 1. Okay, and then the height of a child will guarantee to be the height of the parent x minus 1. So in this case, well, for a subtree rooted on each child, and then it contains, that subtree contains 2 of the black height of the x minus 1 and minus 1 again, that many of the internal nodes. So we are trying to break a subtree rooted on x into 3 parts. So let me draw this here. So say this node is x. Let me write down the x. And then for the x, it has 2 subtrees. So the left subtree and the right subtree. So for each of them, that is a subtree. So to get how many nodes we can have in a subtree rooted on x, and then we want to break it into 3 parts: the x itself, the left subtree, and the right subtree, right? And then for the left subtree and the right subtree, we know the number of the nodes possible will be this part, 2 to the black height of the x minus 1 and minus 1. So that is Well, how many nodes we can have in the left subtree, and the same thing, how many nodes we can have in the right subtree, and plus 1 again, that is the parent node X. So if you want to put all three parts together, and then that will be 2 to the black height X minus 1. That is how many nodes at least we can have in a subtree rooted X. So for so far, we are still considering X to be a root of a subtree. So the next part, if you want to consider the whole tree, and then what will be the case? So we are going to simply assume that X is not the root of a subtree. Instead, it will be the root of the whole tree. So we will have the n, the total number in the tree will be greater or equal to 2 of the black height of the root minus 1. So why? Because we are assuming X is the root. So the next part, we are substituting the black height of the root with the h divided by 2. So why do we do that? Because we have proved that BH, or the black height of the root, will be greater or equal to the h divided by 2. And that is based on the property number 4. Okay, so the next part, starting from here, I'm moving the negative 1 to the right side, and then I'm applying the log algorithm to both sides. So we will have this word. So eventually we want to move the divided by 2 to the other side, and then I want to reverse the right side and the right side, and then I will have this one. So h is smaller or equal to 2 log n plus 1. So what is that? We have proven an upper bound of h, and that is log n, because we can drop the 2 here, we can drop the 1 here, they are both constants. Okay, now that's the important part. We have proven that for a red-black tree, the height is O log n. That's very important. So why? Well, for example, if we want to find the minimum, how to find the minimum of a binary search tree? Well, that is, you want to start from the root, go left, go left, go left, and then until you find a leaf, right? So how many steps are you going to go down? That is the O of the tree height, which is h. And now we have proven the height of the tree is a log n. This means if we want to find the minimum, and this operation is guaranteed to be done with O log n time. And the same thing, the maximum, we just go right, go right, go right, so it can be done with the O log n time. Well, and for the successor and the predecessor, they're the same, and for a search, that's the same too. Okay, so for all those operations, they can be done with O log n time. In the next part, how about the insertion and deletion? Insertion and deletion, let me give you the conclusion. They can also be done with the O log n time. However, for the insertion and deletion, they may break some of the properties of the red-black tree. So we may have to fix the tree a little bit. But anyhow, it is guaranteed for the insertion and deletion, they can also be done with the O log n time. So that's the end of this lecture. So we have learned the red-black tree, and we have proven that the height of a red-black tree, after we enforce all the 5 properties of the red-black tree, and then they will guarantee the height of the tree will be the O log n. If we have a binary search tree with a height guaranteed to be O log n, and then there are a lot of operations can be done in the O log n time, and this is what we love. So even in the worst case, for those operations, they can be done with the O log n time. And remember, for some of the changes, for some of them, they may change the tree, and then we have to fix the tree. However, it's guaranteed they can be done with the O log n time. So this is the end of today's lecture, and I will see you later.